Welcome back. In this video lecture, we're going to cover section 2.5 of the text, two quantitative variables, scatter plot, and correlation. I've divided the section into four subsections. So first we'll look at two quantitative variables, then we'll look at correlation, then we'll look at the important topic of correlation versus causation, and then finally we'll end with a short section on computing correlation. So let's begin with two quantitative variables. Oftentimes we're interested in the interactions between a pair of quantitative variables within each case in the data set. I think it would be helpful to have a concrete example in mind. So in basketball, a rebound is labeled offensive or defensive according to whether the rebound occurred while on offense or on defense. Now using StatKey, let's load the file two quantitative variables NBA players -2e def rebound versus off rebound. This file contains data for each NBA player, including defensive rebounds, notated by def rebound, and offensive rebounds, notated by off rebound. We're going to answer questions on the next slide, but let's look at the data set first and let's look at the visual representation of the data and get comfortable with that. Now we need to be careful at this point. We're looking at two quantitative variables, interactions between two quantitative variables. So we're going to select that, and then we're going to pull in the file, NBA players -2e def rebound versus off rebound. And here's the display. Now let's get comfortable with what's being displayed to us here. First of all, let's look on the x-axis. It's labeled offensive rebounds or off rebounds, and the y-axis is labeled def rebound or defensive rebounds. Each one of these dots in the display represents an NBA player. And when you mouse over the dot and look at its coordinates, what's being given to you here is for that particular NBA player, there were 134 offensive rebounds and 240 defensive rebounds. So as you go from dot to dot, you're moving through different players in the NBA and you're looking at pairings of their offensive rebounds and their defensive rebounds. And this is what's called a scatter plot. It's a way of representing interactions between a pair of quantitative variables. Okay, let's go to the back to the course notes here and look at a series of questions that I want us to answer with respect to that scatter plot. And they're on the next slide here. Let's go to that. Let's look at our first task. We're asked to indicate the direction of association between the variables. And let's just briefly review what the direction of association pertains to. So we would say that there's a positive association between a pair of variables if increase in one variable is met by a sympathetic increase in the other variable. We would say that there is a negative association or a negative direction of association between two variables if increase in one variable is met by a sympathetic decrease in the other variable. So let's take a look at our data and see what we're looking at here. I think we can safely conclude that this is a positive association. What are we witnessing here? We're seeing that as we move through the data here, as the number of offensive rebounds is increasing, the number of defensive rebounds is also increasing. And this, if you think about it, this is not unexpected, right? Because rebounding is a skill, and it's also based on a player's physical traits. If you're tall, you have a greater chance of getting rebounds. If you play a forward or a center position, you have a greater chance of getting rebounds. So rebounding is a skill, and it's clear that that's a transferable skill. So if you're good at getting offensive rebounds, you're probably good at getting defensive rebounds as well. So not surprisingly, we're seeing a positive association between that pair of variables. Next, identify the correlation between the variables in the table of summary statistics. Now, we'll have a lot more to say about this correlation before this section is through, but for now, let's just know where to find the correlation in the set of summary statistics. So associated with a scatter plot is a quantity called the correlation, and in this case, we can see that the correlation is 0.8. Now, By the time we're done with this section, we'll know how to attach some meaning to that value 0.8. But for now, let's just satisfy ourselves to know where to find it in the summary statistics. Okay, if you were told that a player had 200 offensive rebounds for the season, what would be a reasonable estimate for their number of defensive rebounds? Let's take a look at the data. Now, if we look around players who have 200 rebounds, we'll see one here that's got nearly 200 offensive rebounds and a corresponding 324 defensive rebounds. Here's a player that has 203 offensive rebounds, 388 defensive rebounds. Here's one that's got 196 offensive rebounds and 411 defensive rebounds. So if I were told that a player had 200 offensive rebounds, I might guess in the high 300s. Let's say 380, 390 would be a reasonable guess for the number of corresponding defensive rebounds. Now, this is getting towards the concept of regression, where we're trying to use values of one of the variables to predict the value of the other variable, and we'll have a lot more to say about that in the next section. But for now, we're just kind of looking at the data and kind of making an educated guess as to how knowing the first coordinate, in this case being equal to 200, would help us decide what a likely value for the second coordinate might be. Okay, last question. Can we conclude that there is a causal relationship between these variables? Well, let's look at the data. Now, before we address the question of a causal relationship between these variables, let's think about the following question, right? Can we think of the defensive rebounds or the number of defensive rebounds as a response to the number of offensive rebounds? So in other words, can we think of the offensive rebounds as an explanatory variable for the response variable, the number of defensive rebounds? And I think here the answer is yes. We can think of the number of offensive rebounds as giving us a basis for predicting the number of defensive rebounds. So we can connect these two variables as a response to an explanatory variable. No question about that. That can be done. And that would actually be quite helpful. The question here, though, is can we think of the defensive rebounds, for example, as being caused by the number of offensive rebounds? And I would say that based on the data that we have here, we cannot make that claim. Because remember, to make a claim of causality, a causal relationship, you have to control the explanatory variable. And since we did not control this explanatory variable, the number of offensive rebounds, we merely observed it, we cannot make the claim of a causal relationship between these variables. So that brings the end to the questions related to this. Our next task is to study the definition of a scatter plot. So what is a scatter plot? A scatter plot is a graph of the relationship between two quantitative variables. So a scatter plot includes a pair of axes with appropriate numerical scales, one for each variable. The paired data for each case are plotted as a point on the scatter plot. If there are explanatory and response variables, we put the explanatory variable on the horizontal axis and the response variable on the vertical axis. Okay, now what I want to do is look at a sequence of examples of scatter plots and study some questions associated with them. Let's take a look at our first task. We go to StatKey. We're going to open descriptive statistics for two quantitative variables, and we're going to look at the file called Florida Lakes, Mercury versus pH, and we're going to examine the scatter plot. We have two tasks. First, describe the direction of association between pH and mercury, and two, identify the correlation from the table of summary statistics. Let's take a look at the data. Two quantitative variables, and what we'll notice is the Florida Lakes data is the default. That's when you open up the descriptive statistics for two quantitative variables, the Florida Lakes data is sitting there waiting for you. Now, let's just make sure we understand what's going on here. We have pH on the x-axis and average mercury on the y-axis. And when I mouse over one of these points, I'm witnessing a pH and an average mercury. Now, what is the explanation here? What's going on here? The sample is of size 53. 53 different lakes were randomly selected from the lakes of Florida. Now, from each lake, 2 pieces of data were extracted. First, a water sample was collected and the pH of the water was determined. Number 2, some fish were harvested from the lake and the average mercury level was found in that sample of fish. So when we're mousing over one of these points, we're pointing to a specific lake in Florida and we're seeing the pH level paired up with the average mercury level in the fish in that lake. Now, our first task is to see if we can describe the direction of association that's present in this scatter plot. And I think it's not too hard to see in this case that as the pH level is going up, we are seeing a downward trend in the average mercury level. So I think it's fair in this case to say that we are seeing a negative association between these variables. Now, our next task is to identify the correlation, and here it is in the summary statistics. And here we see that the correlation is a negative 0.575. So we've already seen this now in 2 of our examples that when the association between the variables is positive, the correlation is positive. And when the association between the variables is negative, the correlation is negative. All right, that's something that we are going to hit on later. Let's take a look at our next problem. It's very similar to this one. We're going to go to StatKey, open descriptive statistics for 2 quantitative variables, ICU admissions, systolic versus heart rate. We're going to examine the scatter plot, and just as before, we're going to describe the direction of association between these variables and identify the correlation from the table of summary statistics. So let's take a look at that data set. ICU admissions, systolic versus heart rate. So here we have heart rate on the x-axis and systolic on the y-axis. And let me briefly describe to you what's going on in this data set. This is a sample of size 200, and each one of these dots represents a patient that was admitted into the ICU, or the intensive care unit. Upon being admitted to the ICU, the patient's heart rate was determined and the patient's systolic blood pressure was determined. And so each one of these dots represents a patient and that information upon their arrival into the ICU. So this particular patient had a heart rate of 150 beats per minute and a systolic blood pressure of 160. Now, we're trying to do exactly the same thing we did in the previous problem. We want to, first of all, see if we can infer or deduce a direction of association in this data. Now, when I look at this, it looks very difficult for me to discern a direction of association at all. This looks to me like someone just blasted this graph with a shotgun. I don't see a trend in any direction. In other words, as I look at the heart rates increasing, I'm seeing the blood pressures all over the place. I don't see them rising sympathetically or decreasing, falling sympathetically. I'm not seeing any trend whatsoever. So I really can't discern a direction of association between these variables. Now, when we identify the correlation, we are seeing that the correlation is negative, which would suggest that if there is a trend at all, it is a negative association. On the other hand, the correlation is so close to 0, and as we will see, when the correlation is near 0, it is essentially communicating to us that there is hardly any connection between these 2 variables, right? The direction of association is incredibly weak, even though it is apparently somewhat negative. Okay? So, that concludes a couple of problems here, just kind of getting us used to looking at scatter plots, looking at directions of associations, and identifying the correlation from the table of summary statistics. Our next task is to dig in a little deeper on the concept of correlation and get more comfortable with that. So let's look at the definition of correlation. The correlation is a measure of strength and direction of linear association between two quantitative variables, and it is a number that's always between -1 and 1. So, before we go any further, there's two things that are being communicated here. It is the measure of the strength and a measure of the direction of linear association. Okay, when we notate the correlation, there's two different scenarios. One is a correlation within a sample, and one is a correlation within a population. So for the sample, the correlation between two quantitative variables of a sample will be denoted by, or is denoted by, little r. For the population, the correlation between two quantitative variables of a population is denoted by rho, which is the Greek letter rho. Here are some fun facts about the correlation and some things that you'll want to know. All right, the sample correlation R has the following properties. So as we noted already, R is always a number between -1 and 1. If R is positive, that means that the variables have a positive association, and if R, the correlation, is negative, then the variables have a negative association. We've already seen that in the examples that we've have been studying. So we saw a positive association between offensive and defensive rebounds and a corresponding positive correlation. We saw a negative association between the pH and the average mercury levels in the lakes of Florida, and we saw a corresponding negative correlation. Okay. If R is approximately +1 or R is approximately -1, in other words, if R is at its extremities, either out here at -1 or at +1, then that is an indication of a very strong linear relationship between the variables. All right. If we were looking at the scatter plot, it would look like all of the data is lining up on a straight line, either with a positive slope or a negative slope. Okay. If R is very close to 0, that's evidence of very little or no linear relationship between the variables. We saw that in our example of looking at the ICU admissions and comparing heart rate and systolic blood pressure. We saw that there was no apparent relationship between the variables, and that corresponded to a very, very small negative correlation. Okay. R is independent of the scale of either variable. Now, what that's getting at is something like this, that suppose that one of my variables is a quantity, a length that I'm measuring in feet, okay? And then let's suppose that I decide that later on I want to convert all of the units into inches instead, right? Now that's going to take all of that data and magnify it by a factor of 12. So 2 feet would now be in the data set as 24 inches. That will have absolutely no effect on the correlation. So even though I'm magnifying that variable by a factor of 12, the correlation between that variable and another variable will not change. And that's what it means to say that it's independent of the scale of either variable. I'm free to change scales, and that will have no effect on the correlation between the variables. The final bullet point here is that the correlation is symmetric. So when I talk about the correlation between the average mercury level and the pH in the lakes of Florida, that's the same thing as saying the correlation between the pH and the average mercury level of the lakes in Florida. Another way of thinking about it is it doesn't matter which variable is sitting on the x-axis and which variable is sitting on the y-axis of the scatter plot. I'm free to change the ordering of the variables, and it's not going to change the correlation. It's perfectly symmetric in the ordering of those variables. Now, the population correlation rho also satisfies all of these properties. So we should think of these as properties of the sample correlation or properties of the population correlation. Okay. Let's explore some of these fun facts about correlation through a problem. So we're going to launch StatKey. We're going to go to descriptive statistics for 2 quantitative variables, and we're going to look at the file called cricket chirps, temperature versus chirps. We'll come back to these questions and tasks in just a second. Let's take a look at the data set first. So we're going to go to StatKey, 2 quantitative variables, cricket chirps. Now let's get comfortable with the data set. What's going on here? The sample is of size 7, and what we have here are 7 different observations. So on a given day, a cricket was observed, for instance, chirping at 150 beats per minute, and the ambient temperature was recorded at 72 degrees Fahrenheit. So what we have here are 7 different observations of crickets chirping at so many beats per minute and the ambient temperature at that same time. Okay, so that's the data set. Let's take a look at our questions and tasks. What is the correlation? So if we go to the summary statistics, we find that the correlation is very, very close to 1. It's 0.991. So even if I couldn't see the graph of the scatter plot off to the left here, just knowing that the correlation is very, very close to positive 1 would suggest to me that the data are almost forming a straight line with positive slope. Okay, so that's what we could get from just knowing the correlation is 0.991. How would you describe the strength and direction of linear association between these variables? So let's play the game the other way. Suppose that I saw this scatter plot. What would I be likely to conclude just from looking at the scatter plot? Well, we would look at this and we would say that association is positive because as the chirps is going up, the temperature is going up. And since the data is falling almost nearly on a straight line, we would have to conclude that the strength of linear association is incredibly strong. We would not be surprised if the correlation were in fact close to 1. Can we use cricket chirps to explain the temperature? Well, I think the answer is yes. Imagine the following scenario. We're sitting inside our house and we hear the crickets outside chirping at 140 beats per minute. I think we could use this data to build a model that would allow me to say, well, if the crickets are chirping at 140 beats per minute, the outside ambient temperature is probably close to 70 degrees because we have this nice linear relationship between the chirps and the temperature. It would not be surprising at all to think that we could explain the outside temperature or predict the outside temperature in terms of the number of cricket chirps or their beats per minute. So that is a likely way that we could use this data. We could explain the temperature through the cricket chirps. Now, do the cricket chirps cause the temperature? And the answer is, of course not. At least we can't get there from this data. This data is mere observations. This is just observing crickets chirping and recording the ambient temperature. And since we did not take any pain to control the explanatory variable, in this case the chirps, there's no way that we can conclude any causal relationship between the number of chirps and the ambient temperature. Okay? If anything, it is more likely the case that the temperature is the cause of the cricket chirps. And so the causal relationship probably runs, if anything, in the opposite direction. And that is an experiment that we could imagine setting up, subjecting crickets to different temperatures throughout the day or throughout the year, and then recording the corresponding number of chirps. So it's very likely that we could find a causal relationship, temperature causing the chirps at a certain number of beats per minute. Okay, one last thing I want to show you before we leave this example is up here. We haven't talked about this yet, but right at above this summary statistics is this switch variables button. If you switch the variables, it will have the effect of changing the x-axis to temperature and the y-axis to chirps. Now, what I want us to notice here is that when I switch variables, I want us to notice that this correlation is not going to change at all. Okay, so we're going to hit switch variables, and we're going to notice that the correlation is still at 0.991. And this is to just reinforce this idea that we talked about in our fun facts about correlation, that the correlation is in fact a symmetric quantity. So the correlation between temperature and chirps is the same whether I have temperature on the x-axis or whether I have chirps on the x-axis. It doesn't matter. It's a symmetric quantity. Okay, that's enough to be said about this. That concludes this example. And what I want to do now is talk about the very, very important connection or lack of connection, let's say, between correlation and causation. Now, this is just a caution or a warning. You will hear the phrase, correlation does not imply causation, often repeated, especially if you're working in the social sciences. This is a warning. It's warning us, do not deduce a cause and effect relationship between two variables on the basis of an observed association or correlation between them, even if that correlation is incredibly strong. Let's say very close to +1 and very close to -1. So the strength of an association and the direction of the association really have nothing to do with a causal relationship. So the mere observation of a correlation is not enough to imply causality. So just be careful with that. Okay, so just a word of caution on that. Now I want to close these notes with perhaps the most technical part of the section. We're going to look a little bit into how the correlation is computed. How do we ever arrive at that number R from the sample data? This is a little bit technical. We'll get into it a little bit. I'll show you how the correlation is computed. I don't expect you to do a lengthy correlation calculation with lots and lots of data, but I do want you to see how the pieces could be assembled so that that correlation could be computed if you had the wherewithal to do it. So let's dig into how to compute the correlation. All right, computing sample correlation. Let x1, y1 up through xn, yn be some paired quantitative values x and y for some number of cases n. So at this point, if you want something concrete to latch onto, let's think about the very first example we looked at. This might be a player number 1 and his offensive rebounds and his defensive rebounds. And this could be player number 503. This is their offensive rebounds, and that's their defensive rebounds. So for every data point in our scatter plot, we have an x-coordinate and a y-coordinate paired together. So think of each of these as one of those points in the scatter plot. Okay. The correlation between x and y, so in other words, the correlation of that entire scatter plot, is given by the formula R equals S sub xy divided by n minus 1. So if n is the entire size of the sample, in this denominator here will be 1 less than the sample size. Now, what we have to explore in some detail, though, is what is in this numerator. Now, this quantity S sub xy has the following technical formula. It says, for every point from I equals 1 up to n, that means look across the entire sample and add up for each point in the sample the z-score of the x-coordinate multiplied by the z-score of the y-coordinate. So let me try to say that in another way. So for each point in the scatter plot, there's going to be an x-coordinate and a y-coordinate. You need to calculate the z-score of the x-coordinate. You need to calculate the z-score of the corresponding y-coordinate, and you need to take those two z-scores and multiply them together. So each and every point in your scatter plot is going to have the result of forming the product of the z-scores at that point, and then you need to sum across all of those points in the scatter plot. Now, hopefully this will make a little more sense when we look at a specific example, but that's what's entailed in computing a correlation. Each and every point in the data set has a product associated with it, and you have to sum across all of those products to form this numerator S sub xy, and then you need to divide the entire thing by n minus 1, or 1 less than the sample size. Now, let's look at a particular problem to see if we can get our heads wrapped around this. Okay, so here's the problem we're going to study. We've looked at this data set before, so this will be somewhat familiar to you. The pH level and the average mercury level in fish were collected from 53 lakes in Florida, and a scatter plot for the data is shown on the next slide. Let me show you that real quickly. There's the scatter plot for the data. It's these red and black dots here is the scatter plot for that data. The dashed vertical line is the mean of the pH levels, and the dashed horizontal line is the mean of the mercury levels. And 4 particular data points are indicated in black. Let's take a look at that. So what you can do is you can take all of these dots and project them down onto the x-axis and think of them as just the information carried in the pH data. You can see that the mean of the pH data up here, I've put the summary statistics in here, the mean of the pH data is 6.591. So what I did is I drew a vertical line through that mean pH level of 6.591. You can do the same thing with the red and black dots here. You can project them down onto the y-axis. The mean mercury level is 0.527. So I drew a horizontal line through the mercury data at the mean of 0.527. So we've got a vertical line and a horizontal line that are given by the mean levels, in this case, of the pH and the mean levels of the mercury. And what this does is it splits the data into 4 quadrants. You can think of this as quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And what I've done is I've carefully chosen a data point with their corresponding coordinates from one from each quadrant. So here's a sample from quadrant 1, a case from quadrant 2, one from quadrant 3, and one from quadrant 4. For each of the 4 indicated points, calculate its contribution to that value S sub xy. There's S sub xy. We're going to do this calculation. We're going to find this z-score for the x-coordinate, the z-score for the y-coordinate, and we're going to multiply them together. That will be the contribution that will be given from that particular point to the overall value of S sub xy. So there are going to be 4 calculations to do, one for each of those points. And here's what I want us to observe. I want us to show that the signs of the contributions to S sub xy follow the pattern plus, minus, as we move from quadrant 1 to quadrant 2 to quadrant 3 to quadrant 4. So as we work our way through the quadrants and look at those particular points that I've selected, we should see that their contributions are going to be a positive contribution to S sub xy, then a negative contribution, then a positive contribution, and then a negative contribution. Okay? Now we're going to want to observe that, and then we're going to see if we can explain that. And then we want to do one final thing. We want to explain why the correlation of the Florida Lakes data is negative. So in the process of doing this calculation, can we see why, based on how the data is distributed into these quadrants and how the data values are behaving in these quadrants, can we formulate an explanation as to why the correlation is negative in this case? So what I'm going to do is finish this calculation, do these calculations using the overhead camera so that we can see these calculations take place in real time. And so we'll discuss the remainder of this problem just using the overhead camera instead. So join me at the overhead cam for the completion of this problem. All right, so welcome to the overhead camera. Let's take a look at this problem now in some detail. So what do we have to do? For each and every one of these indicated points, one in quadrant 1, one in quadrant 2, one in quadrant 3, and one in quadrant 4, we have to calculate its contribution to the overall value of S sub xy, and hence its contribution to the overall correlation. All right, now here's what that entails. I have to take the 7.8 here, for instance, in this first coordinate, and I have to find its z-score. Now, it's a pH level, so I have to standardize it according to the mean and standard deviation that's appropriate for a pH level. Then I have to do the same thing for the 0.77. I have to standardize it. It's a mercury level, so it has to be standardized according to the mean and standard deviation appropriate for a mercury level. And then I have to take those two z-scores and multiply them together. Okay? And that's going to produce a number. And I want to think of that as the number that's attached to that point. There's a number just like that that's attached to every single one of these points in this array. So we're just going to work it out for 4 different cases, but you have to imagine, let your imagination run wild, and let's just imagine that there's a number like that attached to every single piece of data in this scatter plot. So let me show you in some gory detail how this looks for the point 7.8 and 0.77, and then I'll walk you through what it would look like for the rest of the calculations. I won't show them to you in gory detail, but I will indicate what the calculations look like and how the answers come out. All right, so that 7.8 has to be standardized according to the mean and the standard deviation of a pH level. So that's 7.8. I'm going to subtract the 6.591 and divide by the corresponding standard deviation of 1.288. Okay, that's the z-score of that pH level. Now I need to do the same thing and find the z-score of this mercury level. So I subtract 0.527 and I divide by 0.341. Okay, after you work these out and form their product, this ends up being on the order of 0.669. All right, so the 0.669 is the number that I'm going to attach to this point here. So I'm going to think of that point as not only having this coordinate, but also having the value that we've just calculated, which is 0.669. So think of that number as being attached to that point. Okay? Now, we have to do that calculation for this point in quadrant 2 and quadrant 3, etc. Now, I've done all those calculations. You can see that all that changes as I move from point 1 to point 2 to the point 3 to the point 4 is, since these coordinates change, I have to change out the 7.8 and the 0.77 for 6.1 and 1.23. All other elements of this calculation remain the same. So all I have to do is take this basic calculation we've done and replace those coordinates by 6.1 and 1.23. So it's just a sequence of replacements, recalculations, and reformations of those products. But when we do that, we find that the point in quadrant 2 produces a product of negative 0.785. The contribution from the point in quadrant 3, which has coordinates 5.2 and 0.25, is going to be 0.877. And finally, the contribution from the point in quadrant 4 that has coordinates 7.9 and 0.27 is going to be negative 0.766. Okay, so that's the calculations that are involved. We have to standardize coordinates and multiply the standard scores together to get the overall contribution that each point will give to the value of S sub xy. Now here's what I want to focus on. We just worked this out for one point in each quadrant, and what we saw just by working this out for one point in each quadrant is that this ends up being a positive contribution, this ends up being a negative contribution, this one is a positive contribution, and this one is a negative contribution. I claim that all of the points in quadrant 1 are going to give a positive contribution to S sub xy. All the points in quadrant 2 will give a negative contribution to S sub xy. all the points in quadrant 3 will give a positive contribution, and all of the points in quadrant 4 will give a negative contribution. Let's go back and look at our calculations and see if we can see how that came out to be. For instance, in quadrant 1, our coordinate was 7.8.77. We plugged them in to calculate their standard scores, and then we took the product. Now, what's interesting about a point in quadrant 1 is that both the x and the y coordinates are larger than the mean. That's what it means to be in this first quadrant. You're above the mean in both cases, and therefore, both of these calculations will result in positive numbers, and this calculation will therefore be positive because it's a product of a positive number and a positive number. So any point in quadrant 1 is going to have a positive product when you do the product of the z-scores. Now when you move into quadrant 2, you can see how the situation changes. This coordinate, the 6.1, is below the mean, whereas this coordinate is above the mean. So this is going to have a negative z-score, this will have a positive z-score, and the overall product will now be negative. Okay, so that's why this is negative. In this quadrant, both z-scores will be negative, and therefore their product will be positive. And in this quadrant, one of the z-scores will be negative and the other will be positive, and that's why the product is negative. All right, so the long and short of it is this. All of the points in quadrant 1 are going to be adding positive contributions into S sub xy. All of the points in quadrant 2, negative contributions to S sub xy. Positive contributions, and finally negative contributions. Okay, so now, if you understand that, remember that in order to get the value of S sub xy, I have to add up the contributions from all of these points, and then to get the correlation, I have to divide by n minus 1, which in this case is just going to be 52. So I'm going to take the value of S sub xy and divide it by 52. Let's take a look at what S sub xy is likely to be, right? We're going to have a few positive contributions from quadrant 1, and we're going to have a few positive contributions from quadrant 3. But most of our contributions are coming from quadrant 2 and quadrant 4. That means overwhelmingly our contributions are going to be coming from these two quadrants. So all of these points here and all of these points here are going to be adding negative contributions into S sub xy. And that's why the net effect here is to have a value of the correlation, which in fact is negative. Okay? So when we think about negative correlation, we're really seeing that the bulk of the data is landing in these two quadrants and therefore producing a negative correlation. And when we have a positive correlation, it's because the bulk of the points are in these two quadrants and we're producing an overall positive correlation. Okay? So that brings an end to this calculation. I hope this made some sense to you. We'll talk about it when we get together in class and help reinforce this idea. But I hope you got something out of this nonetheless. So that brings a close to this section, and I'll see you in the next video lecture when we take up the topics of section 2.6. I'll see you then. Take care. Bye-bye.